Welcome to the deep dive. So, if you're tuned in and you're part of the Digital Sciences Master's program at TH Köln, you'll know we're always focused on that end goal, getting usable, performant data to the business users.
Absolutely. And today, we're really diving into a core piece of that puzzle, multidimensional modeling.
Right. It's the foundation for that final delivery layer.
Exactly. Our mission today is to unpack why the star schema, which is really the physical form of dimensional modeling, is the canonical data structure for the information mart and Data Vault 2.0 environments.
It's not just theory, is it? It's about making things work in practice.
Precisely. It's the strategic approach to, well, maximizing query speed and maybe even more importantly, enabling that low-level self-service BI we always talk about, getting business users to answer their own questions.
Empowering them, yeah. So let's start right at the beginning. The core idea of dimensional modeling, what is it, essentially?
At its heart, it's about taking measurements related to business processes and then, crucially, establishing the context for those measurements.
Okay, processes and measurements. How do we define a process here?
To think of a process as any business event or activity, something with a start and ends, maybe some steps in between, and it results in some kind of numeric value.
Like revenue.
Yeah, or even things like session duration, units sold, numeric outcomes. And the dimensional model builds the context around that number, the who, what, where, when, why, behind the measurement.
So conceptually, it sounds quite elegant. You have a single measure, maybe sales amount.
Right.
And then surrounding it, you have all these different angles, these contexts.
Exactly. Like, who is the customer? What customer category are they in? Where did the sale happen? Which branch region? When did it happen? I mean, you could break that when down.
Week, month, year.
Right. And what product category? Through which sales channel?
Yeah.
Each context gives you a different way to slice and dice that central measure.
And when we want to actually build this in a database, a relational database, that's where the star schema comes in.
That's the blueprint. The star schema is how we physically instantiate that dimensional model. And it's specifically designed, really optimized, for user reporting and fast queries.
It has those two main parts, right? Dimensions and facts.
Correct. Dimensions hold the context, the descriptive stuff. Facts hold the measurements, the numbers. And this clear separation is absolutely key for empowering business users.
Why is this structure, this star schema, so much better for reporting than, say, querying the data vault directly or a standard normalized model?
Well, it really boils down to simplicity and performance. It drastically minimizes the number of joins needed for a typical business query.
Fewer joins means faster queries.
Exactly. A user looking at sales data might join the central sales fact table to maybe the customer dimension, the product dimension, and the time dimension. That's maybe 3 joins.
Okay.
In a highly normalized model, or even navigating the DV structure directly for certain types of reporting, you might be looking at, dozens of joins to piece together the same information.
Which is just too complex for most end users.
Right. The star schema makes the structure predictable and easy to navigate. That's the heart of self-service.
Okay, let's dig into those two pillars then, starting with dimensions. The context, the who, what, where, when.
Dimensions hold all the descriptive attributes. Think text, categories, flags. These are the things users filter on, group by, put on the rows and columns of their reports.
And there's a guideline for designing them, isn't there? Something about broad and short.
Yeah, that's a really important rule of thumb. Dimensions should be broad, meaning they have lots of descriptive attribute columns. Think about a customer dimension, name, address, city, state, zip, category, sign-up date. Lots of detail.
Okay, lots of columns.
But they should be relatively short in terms of the number of rows compared to the fact table. You might have millions of customers, but you'll likely have billions of sales transactions.
Got it. And the attributes themselves, what qualities should they have?
Good quality data is paramount, obviously. They should be textual or discrete values, mostly. And ideally, any attributes should be time invariant.
What does that mean, time invariant?
It means the value doesn't change over time, or changes very rarely, like someone's date of birth. That belongs in the dimension.
But not their age.
Right. Age changes constantly. That's usually calculated on the fly in the report or BI tool based on the birth date. You want the stable attributes in the dimension.
Okay, but some attributes do change. A customer's address, their category, maybe their name. How do we handle that if we need accurate historical reporting?
Now we're getting into a critical concept. Slowly changing dimensions, or SCDs. Specifically, SCD Type 2.
Type 2. Why is that one so important?
Because it preserves history. If you just overwrite the old value, With the new one that's SCT type 1, you lose the historical context.
So if a customer moved last month and I run a report on last year's sales,
You'd see their new address associated with those old sales, which is wrong. SCD type 2 avoids this by adding new rows to the dimension table whenever a key attribute changes.
new rows for the same customer.
Yes. Each row represents a specific version of that customer's attributes over a period of time. You add columns like valid from, valid until, maybe an IS valid flag.
So you can join the fact record based on its timestamp to the correct version of the dimension record that was active at that time.
Exactly. It ensures temporal accuracy in your historical analysis. Absolutely vital for reliable self-service BI.
Makes sense. And I think there are other techniques for dimensions too, something called role-playing dimensions.
Oh yeah, that's more about efficiency. It's where you have one physical dimension table, like a time dimension, dim time, but you use it multiple times in your fact table, linked via different foreign key columns.
Give me an example.
Okay, in an order fact table, you might have an order date key, a require date key, and a ship date key. All three of those foreign keys point back to the same dim time table.
Ah, so you don't need 3 separate date tables.
Exactly. The dim time table is playing different roles in the context of that fact record.
Yeah,
Saves space, ensures consistency.
clever. Okay, let's switch gears to the other pillar, fact tables, the how much.
Right, these are the tables that hold the actual measurements, the numeric values we want to analyze. And they follow the opposite design principle to dimensions.
So if dimensions are broad and short,
Facts are narrow and long. Narrow because they typically only contain the foreign keys to the related dimensions and the numeric measures themselves. Very few columns.
and long.
Very, very long. This is where the bulk of your data warehouse rows will be. Millions, billions, even trillions of rows in large systems. Each row represents a specific measurement event at the lowest grain.
Now, the most critical aspect of the numbers in the fact table, the measures, is their additivity. You mentioned this earlier.
Yes, this is fundamental for BI tools. If users drag a measure into their report, they expect to be able to sum it up, average it, etc., across different categories.
Yeah.
The additivity determines if that's mathematically valid.
So what are the types of additivity?
There are 3 main types. First, fully additive. These are the best kind, the gold standard. Measures like sales amount, quantity sold. You can sum them up across any dimension without restriction.
Sum sales, by time, by product, by customer. It all works.
Correct. Then you have semi-additive measures. These are common, but need care. They are additive across some dimensions, but not all.
What's a typical example?
Inventory levels or account balances. You can sum inventory across different products or warehouses for a given point in time. But summing inventory levels across different months, that doesn't make sense. It's non-additive across the time dimension, usually.
Right. The sum of monthly closing balances isn't meaningful total inventory.
Exactly. So semi-additive, and finally, the dangerous ones, non-additive measures.
Things like ratios, percentages.
Precisely. Things like profit margin percentages, temperature readings, or any kind of pre-calculated ratio like return on investment, ROI. These cannot be meaningfully summed across any dimension.
What happens if someone puts, say, ROI directly into the fact table?
Well, if a user tries to aggregate it, like summing the ROI across all products, the result is just garbage. Mathematically meaningless and worse, actively misleading.
So where should those calculations happen?
They must be calculated at the reporting layer, in the BI tool itself, or potentially in a higher-level aggregate fact table. You keep the base additive components in the main transaction fact table, like revenue and cost, and calculate the ratio, ROI, later.
Keeps the core fact table clean and ensures analytical integrity.
Absolutely. Performance and correctness depend on it.
Okay, fantastic. Now, let's talk about the different types of fact tables, because their structure, especially the primary key, depends on the granularity of the process they're measuring.
Right. The grain determines what a single row in the fact table represents. There are 3 main patterns.
Let's start with the most common one, the transaction fact table, or TFT, sometimes called an event fact table, EFT.
This is the simplest, most fundamental type. One row equals one single atomic event or transaction. Think one line item on an order, one click on a website, one phone call record.
So its primary key uniquely identifies that specific event.
Yes. And it will typically contain foreign keys to all the relevant dimensions. Usually one timestamp column indicating when the event occurred, and then 0 or more numeric fash columns, the measures.
The football game example was good. Each row is a specific event, like a shot, pass, goal.
Exactly. And these are often populated using a PUSH pattern directly from an operational system. Like every time an order line is confirmed, a row gets pushed into the order line's transaction fact table. It's often a one-to-one relationship from the source event.
Is the factless fact table related to this?
Yes, it's essentially a transaction fact table, but without any numeric measures. It's used just to record that an event happened.
Like tracking which students attended which lectures.
Perfect example. There's no number to measure, but the relationship between the student, the lecture, and the date is the important thing to capture. You're marking an occurrence.
Do they usually have any facts at all?
Sometimes, to make querying easier, people add an artificial fact column, often just called count or something similar, and populate it with the value 1. That way, users can easily sum that column to count the occurrences.
Okay, makes sense. Now, the next type sounds more complex. The Accumulating Snapshot Fact Table, ASFT.
It is definitely more complex conceptually and technically. The focus shifts completely. Instead of one row per event in an ASFT, one row tracks the entire life cycle of a single process that goes through well-defined milestones.
So not individual sales, but maybe the entire process of handling an insurance claim or a student's journey through a degree program.
Exactly. One row represents one claim or one student's enrollment. That single row gets updated over time as the process moves through its stages.
That implies a different structure for time then, not just one timestamp.
Absolutely. An ASFT requires at least 2 timestamps, typically a start date for the process and a date representing the current status or the completion date. Plus, you'll often have specific date keys marking when major milestones were completed.
And the facts.
You'll have facts related to the overall process, and importantly, facts that measure the duration between milestones. How long did it take to get from stage A to stage B?
And the update pattern must be different too, not just a simple push.
Drastically different. It usually starts with a PUSH when the process, like the claim, is initiated. But then, as milestones are reached or data changes, you need subsequent PUH or even PULL processes to find that existing row for that specific claim and update it.
So many source system events update one single row in the ASFT over time.
Right. It's an endpoint-one relationship from source events to the ASFT row. Tracking that life cycle within a single row is the key characteristic.
That persistence and updating in place is quite distinct. Okay, finally, the Periodic Snapshot Fact Table, PSFT.
The PSFT changes the grain again. Here, one row summarizes the status or performance of multiple events or processes over a specific, regular time period.
So not individual transactions, not a single process life cycle, but an aggregation over time.
Exactly. Think monthly sales totals for each product and customer combination, or maybe daily inventory levels for each warehouse. You're taking a snapshot at regular intervals.
What does the primary key look like then?
The PK is typically a composite of all the foreign keys, including a foreign key to the time dimension that represents the period, like month-end date, not a specific event timestamp. There's exactly one reference to the time period per row.
So it's inherently summarized data.
Yes, designed for consistent period-over-period reporting and trend analysis.
This is great. Really clarifies the different ways to model measurements. Now let's bring it back to the bigger picture, especially for the students at TH Köln. How does this fit into the overall data vault pipeline?
It's crucial to understand the layers. In the approach often taught, the core data warehouse layer uses the data vault model hubs, links, satellites. That layer is optimized for integration, auditability, historical completeness, and flexibility to change.
Built for resilience and capturing raw history.
Right. But it's not typically optimized for end-user querying performance or simplicity. That's where the next layer comes in.
It's the information mart layer.
Exactly. And that's where we build our star schemas using dimensional modeling. The Information Mart's sole purpose is to take the integrated, audited data from the data vault and reshape it into these highly optimized, user-friendly star schemas specifically for reporting and BI.
So the star schema is the bridge, the delivery vehicle to the end user.
Precisely. It translates the complexity of the core DW into something intuitive and fast enough for self-service analytics.
Okay, let's get specific then. How do we actually source the star schema components from the data vault components if I'm building a dimension table?
Okay, the dimension grain, the unique identifier for your dimension row, like customer ID, that comes directly from a hub in the data vault because hubs store the unique business keys.
Makes sense. And the descriptive attributes, the broad part, name, address, category.
Those come from the satellites attached to that hub. Satellites store the descriptive, time-varying attributes associated with the key in the hub.
And if I need SCD type 2?
Then you'll typically query all the historical records from the relevant satellites for that hub, using the load dates in the satellites to construct the valid from and valid until periods in your dimension.
Got it. Hubs give the key, satellites give the context and history. What about the fact table? Where does its grain come from?
The fact grain, the fundamental relationship or transaction being measured, is usually derived from a link table in the data vault. Links represent the associations or transactions between business keys, which are stored in hubs.
Like a link connecting an order hub and a product hub represents an order line item.
Exactly. That link establishes the relationship that becomes the grain of your transaction fact table.
And the measures themselves, the numbers.
The numerical measures metrics typically come from satellites attached to the links, often called link satellites. These hold the quantities, monetary values, or other metrics specific to that transaction represented by the link.
Or sometimes pre-calculated.
Yes. In more complex scenarios, measures might come from computed satellites or even specialized structures like aggregate links, where some calculations are done within the DV layer to optimize downstream processing.
So, pulling it all together, what does this mean for someone trying to enable genuine self-service BI?
It means the star schema isn't just, throwing some tables together. It's a very deliberate, engineered structure. You're applying specific rules about measurement context, about granularity, and you're sourcing it methodically from that robust, auditable data vault foundation.
It's the translation layer that makes complex enterprise data usable.
Usable, understandable, and performant enough for business users to explore it themselves without needing an IT intermediary for every single query. That's the goal.
Which brings us to a final thought for you, the listener, to ponder. We've emphasized these rules, dimensions broad and short, facts narrow and long. We talked about avoiding things like very fine-grained timestamps and dimensions.
Right. So the question is, why is strictly following these structural rules, this specific shape of the star schema, the single biggest factor in boosting performance and flexibility for self-service BI? It's not just about saving disk space. Think about how a database query optimizer works when faced with joining a massive fact table to several dimension tables based on user selections. Why does this particular structure make that process so much more efficient?
Something to think about as you design your own information marts. The structure is the strategy for performance.